simply filtering, right? Simply filter out using band pass filter, right? Your one of the sideband will be removed, right? Okay, I have explained you about this in the last class. Hope you all understood about this. Okay, simply frequency domain filtering. We can remove the one of the sideband. Okay. See, having or designing a filter for a sharp cutoff is very, very difficult. Those who are taking DSP, you will understand how difficult it is to design a filter which has a sharp cut. Right. Okay. See, I will draw this spectrum. Okay, this is the spectrum of the. I consider spectrum something like this. Okay. This is B, this is minus B. This is your M of B. Okay. This is your M of A. Spectrum of the modulating signal or measure signal. Right? This is F. Okay. Hope all of you understood about this spectrum, right? See, spectrum looks like this, means these are the frequency components. Maximum frequency of the signal is B. Okay. Now, all of you know that after double sideband, suppress the carrier modulation. Okay, so it will become a passband signal. Let's say C and somewhere minus C. So it will become, suppose if its amplitude is 1 here, it will become like this. Fine. This amplitude will become up. Fine. Okay. This is actually spectrum of DSBSC waveform. This is F in part. Right. Okay. Now, out of these, you all know that this is FC plus B. This is FC minus B. This portion is upper sideband, right? This portion is upper sideband. Okay. And this portion is lower sideband. Similarly here, I'm not going to draw this side. Okay. Now, if I want to remove one of the sidebands, okay, you have to use a band pass filter, right? You have to use a band pass filter. So I will draw the band pass filter frequency response here. Once again, F in pass. Okay. So this is your upper sideband. This is your lower sideband. Okay. Now, your band pass filter will be something like this. See, I am going to keep only upper sideband, remove only lower sideband. See, this is the band pass filter. This is 0, 0, 0, and this is going to be 1. Okay. This is your band pass filter. Okay. I'll write this right. Band pass filter. What is the cutoff? What is the lower cutoff? Lower cutoff is FC. Upper cutoff is FC plus FC. Right? Lower cutoff is FC. Upper cutoff is FC plus D. Fine. Okay. Now, you have this is minus FC. Okay. And you have FC minus D here. Okay. Now, what happens if you multiply this? You know that filtering is going to be multiplication in frequency domain. All of you know that. Okay. That means you are multiplying this and this. Right? So when I multiply this, I'm talking about some ideal filter. This filter which I'm drawing is an ideal filter. We're assuming that filter is an ideal filter. Okay. Now what you get here is SSB of, I'll just USB, upper sideband of here. 0. This is F in. Now once again here, I'm just going to draw that. This is going to remain. So what you'll get here is only upper sideband. I'm using board, so please spin to the board. Now here you have FC, FC plus B. Okay, minus FC, minus FC, minus C. Now, what is the problem with this? Why we cannot effectively use this particular filtering method of generation of SSTD? This is very easy, right? You discard one band, one frequency band using filters. See, what I have drawn here is an ideal filter. Ideal filter, right? This is ideal filter. Ideal filter means it has a sharp cutoff. I think in DSP you must be studying this, right? Yes or no? What is an ideal filter? Okay, anyway, at least those who are in DSP. What is an ideal filter? What is an ideal filter? No. Okay. Ideal filter means cutoff is very sharp cutoff. Can you see here? In this filter, this is a band pass filter which passes band of frequency between FP to FP plus FB. See that it is sharp cutoff. According to this frequency, this is called frequency response. Okay, or transfer characteristics in the frequency domain. Okay. Now, if you see this, okay, it has a sharp cutoff, but this is not possible practically to realize. For writing with a pen, theoretically okay, but this has to be implemented, right? You cannot have a sharp cutoff because ultimately this is implemented using capacitors, op-amps, resistors, yes or no? Right. Now, if you see the frequency response of this RC circuit, okay, you will never get a sharp cutoff. Right. Always you will get a frequency response something like this, right? This also you get something like this. Now, in such cases, can you see, is it possible to have a exactly FC plus FB to be removed? No. So filtering method theoretically accepted, okay, but practically it has a problem of both, because it is not possible to realize ideal filter. I've understood this. Okay. Now we need some other method to do this. Okay. Some other method which is used, we call it a Hilbert transformer method. Hilbert transformer method. We'll see. Hilbert transformer method is very simple. Name looks slightly complicated, but the theory is very simple in this. Okay. So have you understood this? This is called filtering method. Right? Now suppose if you want to keep LSB, remove USB, your band pass filter will be here. Okay? This will not be there. Okay? Now, to understand, okay, now can you tell me what is the bandwidth of this now? Suppose if I use this, this is actually upper sideband. What is the bandwidth of this? What is the bandwidth of the upper sideband? That is SSB signal. What is the bandwidth? See here. What is the bandwidth for here?
B, sir.
Fc minus Fc. How much? B
B.
half. No. Bandwidth is actually the band of frequency occupied. In the case of double sideband suppressed carrier, bandwidth is 2B. Why 2B? Because Fc plus B minus Fc minus B. It will become 2B. This is the band of frequency. Band of frequency means this frequency minus this frequency is equal to this band of frequency. That is 2B. Right. See here. Double sideband suppressed carrier wave has a bandwidth of how many hertz? How many hertz? 2B hertz. Here, how much bandwidth you can save? 2B hertz. Now, what is the bandwidth of this single sideband wave? It is just B. The benefit. Is the benefit. Can you tell me? I want to ask you a question. Why bandwidth is very important? Saving bandwidth is very important. Why we need to save bandwidth? We're talking about saving bandwidth, right? You know, save water. Why to save water? You all know, right? Save electricity. You know why save electricity, right? Yes. See, when you transmit a signal, right? This channel has got a limited bandwidth. And in that limited bandwidth, okay, many people want to communicate. Yes or no? Everybody wants to communicate nowadays. Wireless, everything. Right. Now, your AM wave itself occupies 2B hertz. Okay. Just imagine. 2B hertz is occupied, right? Nobody can occupy that bandwidth. Yes or no? Right. So now, instead of 2B hertz, in double sideband suppressed carrier wave, your bandwidth is 2B hertz. Now, you are actually transmitting AM wave using single sideband modulation. When you use single sideband modulation, your bandwidth is reduced to B hertz. See what is savings you get in there, because that remaining B hertz, which was occupied by this, can be used for some other purpose. I understood. Okay. So one benefit of single sideband modulation is saving bandwidth. Power you don't know, but bandwidth is definitely saved. Right? Okay. Power you can see now. Let us see what is the power. Right? Okay. Now, let us come back to the expression of double sideband suppressed carrier wave. Right. Let us come to, I will just rub out this. Okay. Hope everybody has taken it. Okay. I have recorded this session. You can just, I'll share it with you. Okay. If at all you are not taken it down. This is filtering method. Okay. How important this communication system is. I just came into my mind. No artificial intelligence will work if your communication system is poor. Do you accept it? Right? Yes or no? Right? So that's why communication systems are very important aspect than anything. Right? So whole world says that it is going behind artificial intelligence, deep learning, everything. But if the communication system itself is not there, that's why both are going hand by hand. How many of you attended that 6G lecture which I have communicated to you? Hope you remember, right? I have forwarded one link for a lecture series on 6G communication. Right?
Yes, sir.
You just go through that because that is going to be the future communication. Okay. I don't know whether your artificial intelligence is going to be there or not, but communication will be definitely there. This generation communication is going to happen, right? Just go through that. If time permits, we can just attend that lecture. Okay. Okay. Suppose your m of t is equal to AC cos omega ct. What is this? Tell me. This is a single tone wave, right? And your carrier signal Q of t is equal to, sorry, this is AM, supposed to be AM, supposed to be WM, because it is pressure signal, AC cos of omega ct. This you know, right? Okay. So can you tell me the expression for double sideband suppressed carrier expression? I'll just write like this. How do you generate double sideband suppressed carrier? I told you it's very easy, just a multiplier. This is your m of t and this is your c of t. Right? Fine. Okay. Now, what you get here is double sideband suppressed carrier. Fine. Now, can you just write an expression for this? This is going to be AM cos omega mt into AC cos omega ct. Cos A plus C cos A minus C, right? Right. Okay. So this is equal to AM AC by 2. Okay. AM AC by 2 cos omega mt. Sorry, cos of, I'll just, okay, cos of omega m plus omega c into t. Okay. Or else you can write cos 2 pi fc plus fn into t. You can write like that also, not a problem. If you want to write like that, I will write like that. Cos of 2 pi fc plus fm into t, okay, plus sin am ac by 2, right, cos of 2 pi fc minus fn into t, right? What is this? This is BSPS series, right? Okay. Now, this is going to be your upper sideband. This is going to be your lower side, right? Right. So can you tell me what is the power in this? I want the power in double sideband suppressed carrier give. These are sidebands, right? What is the power in double sideband suppressed carrier give? Suppose, see, take AM AC by 2 outside. Right. Okay. This will become AC square AM square divided by 4. Right. So this is, take the RMS value of this. Right. AC square AM AC by 2, half is already there. Take AM AC by root 2 whole square, right, divided by R. R is 1. So what is the power in the, now I'm just going to write power in double sideband suppressed carrier AM wave. Can you tell what is the power now? Right. See, AM square AC square divided by 4. By considering R is equal to 1 mole. AM AC by root 2 whole square by R. Right, that's going to be the power. Okay. Now, what is the transmission efficiency for DS2 AC waves? This 2 is there, no? AM AC by root 2 whole square divided by this 2 is there. So it becomes 4. Right? Okay. Now, what is transmission efficiency? Tell me, do you remember? Transmission efficiency is power in the sideband divided by total power, right? So, transmission efficiency, power in the sideband divided by total power. Now, can you tell me what is power in the sideband now? This one will be, right? What's the total power? This one will be. Total power is that one only. So, what is the transmission efficiency now? It is going to be equal to 1, which is equal to 100%. Yeah. Power in the sideband. I'm not taking one sideband. I'm taking sideband. This has both the sideband. I'm not talking about single sideband. Right? I'm not talking about single sideband. I understood this. This is the power in DSP-SCB. That is equal to sideband power. Because in DSP-SCB, we have only sideband, no carrier component there. What is the total power? Total power is that only. And the efficiency, transmission efficiency equal to 100. Transmission efficiency is equal to 100. Right. Okay. Now, what is the expression for lower sideband? This is the expression for lower sideband, right? Fine. What is the expression for upper sideband? So now, I'm interested in only one of the sideband objects. I'm interested in only one of the sideband. Right. So I will write a general expression for single sideband. Right. I will write a general expression for single sideband wave, and I'll just rub off this. So now my expression for single sideband, okay, is equal to, okay, this is the expression for double sideband. I will write same thing, AM AC by 2, okay. I will write cos of 2 pi, okay. I will write FC plus or minus FL, where this plus for upper sideband minus for lower sideband. Yes or no? Right? Yeah, this is lower sideband, right? I'm writing plus or minus. If you keep plus, it is upper sideband. T, no? T is there, definitely. T is there. I'm sorry. Sometimes I may miss something. Please remind me. Thank you. Right? So this is the expression for single sideband wave. All of you understood this. Okay. Now let us consider this one of the sideband and let us expand that. Okay. Let us consider one of the expression and let us expand. Okay. So I will rub off this. Okay. Now I will consider only upper sideband. Okay. Expression for upper sideband, see, upper sideband of T is equal to AM AC by 2, okay, cos of 2 pi FC plus Fn into T. Right? Let us consider only one. Can you expand that? Can you expand this expression? Can you expand this? Cos A plus B. Cos A plus B. Do you remember? Are you sure? Let us see cos A plus B. Best method. What happened? But you can't do this in exam. Okay. Now tell you what cos A plus B. Cos A cos B minus sin A sin. Right. Okay. Cos A cos B minus sin A sin. Now this will remain as it is. Okay. Cos 2 pi FC T cos 2 pi F MT, yes or no? Right? Then plus here, plus or minus you? Yeah, minus, exactly. Sorry. Minus sin 2 pi FCT sin 2 pi FM into. Fine. Can you tell me what is the expression for lower sideband? Same thing is a plus, right? So I will write this. In general. I'll remove this as a USB. I will write this as SSB. And what I will put here? I will put. What is this actually? What you see here, this is the expression for. This is the expression for SSB wave. Expression for SSB wave. This is also equal to AM cos 2 pi FM into T. This is also equal to AC cos 2 pi FC into T. Right. Okay. Now, A and AC I have taken myself. What is cos 2 pi FCT? What is AM? Sorry, what is AC cos 2 pi FCT? It is M of T, right? It is. So I'm just trying to simplify this. What is AC? I'll just multiply. What is AC? AC cos 2 pi FCT? It is M of T. Sorry, it is C of T. Right? It is your C of T. Right? Similarly, you have AM cos 2 pi FM, that is M of T. Right. So this is the expression for AM. Now you can see here. Here you have. If you can you get back this one? Purpose of expanding this is represent this signal, okay, with some phase shift. Right, if you cancel, we get back this one. Okay, that's why the purpose of expanding this is to see you that you have a signal which is the 90-degree phase shift of the signal what you have here, right? Which is the 90-degree phase shift of the signal you have here. If you have cos 2 pi fct, right? You have cos 2 pi fct. You already have that with you, right? That is going to be your this one, right? What is sin 2 pi fct? Tell me, what is sin 2 pi fct? Sin 2 pi fct is the phase shifted version of cos 2 pi fct. Yes or no? I understood this now. Now, what is sin 2 pi fmt? Phase shifted version of this one. I understood this. Now, tell me now, this equation generates single side band wave, right? Yes or no? You agree, right? You have cos 2 pi fct in your hand, carrier signal. Yes or no? You have cos 2 pi fmt in your hand. Yes or no? Yes or no? Tell me. Both of that you have in your hand. Yes or no? It is given to you. Come on. Now, to generate a single sideband AM wave, what else is required now from this equation? Tell me. This is there with you, this is there with you. Right. This is there with you, this is there with you. What else is required? Phase shifter, yes or no? You need a phase shifter, yes or no? Come on. Right? What is this tell me? Phase shifter version of this. What is this? Phase shifted version of this. I understood this. Right. So now, if we have a phase shifter, right? Phase shifter means what? Your input is going to be equal to, this is your phase shifter. Okay, this is your phase shifter. How much? What is the phase shifting happening there? 90 degree. That's what. So phase shift by pi by 2. Suppose if you give sin 2 pi fct, what you get here? 90 degree phase shift. Cos 2 pi fct minus pi by 2, how much? It is cos. You get cos 2 pi fct. You get cos 2 pi fct. Right? I've understood this. Okay. Now, can you tell me, to generate SSD wave, I have one line. This is your m of t, which is equal to am cos 2 pi fmt, and you have another one line, that is your ac cos 2 pi fct. Okay. So how do you generate SSD wave? Come on, tell me. You need to have multiplier there, right? Now this is multiplied directly here. Now you have multiplier here. This is multiplied directly. Sorry, multiplier. Multiplier. Now see here. Now you have to generate one. Put phase shifter here. Pi by 2 phase shifter. Right? pi by 2 phase shifter. Okay. Now this cos 2 pi FCT, okay, this what you get here is sin 2 pi FCT, right? And if you put a phase shifter here, what will you get here? Sin 2 pi FCT, right? Okay. Now properly place this. You put multiplier here. Sorry, multiplier. Put a multiplier here. Okay. And then you just take this, okay, pass it through phase shifter, pass it through phase shifter, right? Now multiply. Sorry, I'm not drawing this block diagram in proper form, okay, but hope you're understanding this, okay. Multiply this. Now after that, what you require? And one add it. Sorry for I don't have space here. So now this minus this, right? This is the adder, this is plus, this is minus. Okay. This is phase shifter. Phase shifter means what? If you give sin theta, output will be cos theta. If you give cos theta, output will be minus sin theta, like that. Okay, I understood this. Okay. This one, yes, of course, yes. This is plus, this is minus. Okay. Now, what will be the output from here? Okay. Whether it affects your upper side band or lower side band.
Sir, we cannot see that side of the board. So,
You understood Dubai Road? Huh? This one is implementation of this. Okay. Don't worry, I'll explain you once again. Okay. See this equation. Okay. This equation you understood, right? And I told you that cos 2 pi FTT is a carrier signal, right? Now in this expression, you also have sin 2 pi FTT. How do you get sin 2 pi FTT from cos 2 pi FTT? Just by shifting that wave by 90. Right. So there is a circuit available for that. All of you know that, right? Phase shifter circuit. In microelectronics, you have done it, right? Phase shifter. It is possible to shift the phase of a sine wave by passing it through a transistor circuit. Output will be phase shifted by pi by 10. That is going to be our cost. Or cost will become psi, sine will become cos. Okay, you know that. Okay. Now this will be available through phase shifting this, right? Similarly, this will be available through phase shifting this. Have you understood this? Okay. Now, how do you implement this using block diagram? Suppose if I ask you to implement this using block diagram, in control systems, you will implement an expression using block diagram, right? Okay. So, this is your M of t. Okay, that is equal to, that's what I drawn here. That is equal to cos AM cos omega t, right? Now, this is AM cos of omega mt. Right, and you have C of t, that is AC cos, this I will write 2 pi f mt, this also I will write 2 pi f ct. See, this is AM cos 2 pi f mt, AC cos 2 pi f ct. Right, okay. Now, for time being, what we can do for time being to implement this, consider your AM and AC is equal to 1. Consider your AM is equal to 1 and AC is equal to 1. Right? So what you will have in that case? You will have only cos omega mt cos 2 pi f ct. Right. Now, see, suppose I will just write it in a round oscillator. Round inside the cos 2 pi f ct means it's an oscillator. Okay. One expression is multiplication of cos 2 pi f ct and cos 2 pi f mt. Now use a multiplier. Is a multiplier. Right? So what we will get here? This expression, right? Right. Now take a connection from here. Take a connection from here. Pass this through a phase shifter. What is this? I will write pi by 2, pi by 2. Phase shifter. Phase shifter. Okay. I understood this. Okay. Now you take the output and pass it through a multiplier. Now here you use an adder. Right? Now here you just plus, here you make it minus. What you get here is upper side band. I'm taking minus 2. So what you get here is S of upper side band of T. This is one way of generating. I've understood this now. This is upper side band. This is the expression for upper side band, which is quite straightforward here, right? AMAC, hope you understand how we got this, right? Upper side band is cos 2 pi fc plus fm of t. Just expanding this. I'm just putting it as a cos a plus b. When you make cos a plus b, okay, you'll get this. That's any doubt? Doubt is clear. Okay. I think first straightforward, right? So this block diagram is an implementation of this, nothing else. Only I use here is the phase shifter. One phase shifter is used here. Right. And the phase shifter, okay, the principle behind the phase shifter we call it as Hilbert transform. Hilbert transform. Hilbert transform is a type of transform which gives you the output as a transform the output as a phase shifted version of the waveform. Okay. So have you understood?